So my name is Ruadhán Stokes. I'm a data scientist at Channel 4. I'm going to be talking through some research I did kind of in conjunction with UCL last year on forecasting television ratings. We'll probably start off with a bit of a quick introduction to like the TV market and the ad market and why forecasting is important. We'll move on to some characteristics of the data. We'll plot some like temporal effects and program effects of the data to get a kind of a feel for it. And then we'll move a bit more into the modeling. How do we tie those things together? We'll look at how we deal with changing distributions in the data. So when the distribution of a program's ratings are changing, how do we deal with that? Starting off with simple forgetting or kind of just basically downweighting older data. And then we'll show that the extension of standard forgetting to the Bayesian case is actually really, really simple and actually kind of it opens some doors to kind of like new and interesting methods of estimating what's the best kind of forgetting factor we should be using. Because until quite recently, there hasn't been very much guidance about like how do we decide how much to forget old data. And it kind of, I suppose the takeaway is A, that forgetting is like quite effective and quite simple, and B, that I think it's quite nice because we'll show that by kind of turning the screw of like probability theory and information theory, we come out with like really intuitive and kind of pleasing results for ways of estimating the forgetting factor. So we'll start off with the introduction to kind of the ad market. So firstly, I guess, what is it we're predicting? We're predicting a TVR. So one TVR represents 1% of a population watching a program. So if 10% of all people are watching TV, 10% of them are watching Channel 4. Channel 4 gets a TVR of 1%. So it's quite straightforward. It's kind of on the like 0 to 100 or 0 to 1 kind of interval. Really important thing is how we measure this. So like the ad market in TV can't really exist without measuring this quantity really well. So actually the advertisers and broadcasters put quite a lot of money into doing this in a kind of transparent way that they're both happy with. And this is a thing called BARB, the British Audience Research Board. So they have kind of a big panel of about 51 homes that are chosen to be representative throughout the UK. And they've got like hardware in their homes and they do loads of monitoring. So apart from monitoring how many people are watching, kind of the most important thing that really gets measured is who is watching. So definitely, particularly from the advertiser's point of view, they're really, really interested in not just how many people, but specifically the who. Typically an advertiser or a brand, they're really only interested in kind of like zeroing in on and targeting like one specific subset of the population. I mean, like BMW probably know that no matter how many ads I see of theirs, I can't afford to buy BMW. So they're kind of really keen to just like really zero in on people who they think are actually going to buy their products. And this is kind of, so forecasting the who as well is kind of the key to demographic targeting in television. So there's 16 actual fixed audiences you can buy. So you can buy like ABC ones or upmarkets. So that's actually defined as just if you work at a desk. There's also housewives, which can be male or female, but it's defined as the person in the house who typically does the groceries. So you can see it's a little bit dated. You can see how old the TV industry is. But the important thing is that a brand just picks one of these, and then they only pay for impressions from that audience. So I guess a good example would be if BMW come to us and they say, we want 5 ABC One TVRs, and we'll say, yeah, that's fine, we can deliver that. And then for whatever reason, we decide to put their ad in an episode of like The In-Betweeners, a really young show. And 1 million young people watch that, but only 200,000 ABC Ones watch it. We only get paid for the 200,000 ABC Ones, and we didn't get paid for the 1 million youngs that watched it. So we should have bought a young ad in that place. And you're talking about pretty significant amounts of money for like a 30-second bit of advertising. I think cost of one young TVR, you're probably talking about like nearly £10,000. So yeah, you stand to lose quite a lot of money some of the time. So that kind of puts it into context, like why we're interested in this. So we'll do a bit of visualization of the data now. So here's a subset of like broadcasts. On the x-axis, we've got the young rating, so percent of 16 to 34s that watch the program. On the X, or on the Y, we've got ABC1, so kind of up markets that watch the program. You can see it's quite like multimodal. The line down the middle kind of shows like where it's about the same, where it's about as many ABC1s are watching as youngs. You'll notice in the top left, we've got a cluster where it's like really, really skewing like up market in a big way. And like you need to notice that that cluster there is about 10 times more valuable if we place an ABC1 ad rather than a young ad. So if we place a young ad in any of those top left broadcasts, we're probably losing tens of thousands of pounds, possibly even hundreds of thousands of pounds. So that's kind of to, I suppose, visualize what I've been trying to, the point I've been trying to make. Now we're going to kind of layer on the program information, and that's going to show us something nice. It's going to show us that like knowing what the program is very predictive of like what the ratings are going to be. So if we layer it on, this one in the top left that we were looking at, shock. Young people don't like canals that much. So, I mean, I guess anyone could have probably told you that. But it's kind of nice from a forecasting point of view. It means, like, we know Great Canal Journeys is always going to skew old. So I think old and rich, I mean. So I guess the takeaway from these kind of two graphs is that past program performance is a really strong predictor, and it's something that really needs to be incorporated in any model we look at. So I think the next thing we'll look at is some kind of temporal characteristics of the data. So we'll look at like, this is a week's just like a random week of data colored by day. You can clearly see where the weekend is. The last 2 days, it's like much more daytime viewing, not as much in the nighttime. And then kind of, you can see the daily things peaking at about 8 or 9. So you can see there's strong like time of day effects. The interesting thing is Gogglebox was on Fridays at peak at this time, and it was just doing insanely well. So I think the shocking thing about this graph is that 8% of ABC1s would rather watch people watch TV than go out and do something on a Friday night. So that's kind of a bit of an outlier, that Friday night rating. So we'll look through then the seasonal, like during the year, as you'd expect. Basically, it starts off high in the winter and kind of slowly declines as the weather gets better. That's not surprising at all. The interesting is you can really distinctly see August when the schools go on break, and everyone just like jumps ship from England, which is just right, this big trough there. So I suppose looking at those two things, the main thing is we need a way that like ties together kind of time-based predictors and other things like genre and repeat status, along with the past ratings of like the programming question. That's what that slide says, basically. We also want to be able to, so it's important that if we have a show that we've never seen before, we can still make a good prediction in the like cold start case. So that's quite important as well. So one of the main models that's proposed in the literature is a random effects model. So this is quite a good model if you've got like repeated measurements from different groups. It sort of decouples like the time effects and the genre effects from like the program-specific effects. So you've got the kind of fixed effects, which would be like genre, time of day, which is X, and then the delta P is program-specific. So you're kind of saying that we expect all programs to react the same way to a change in time of day, or like day of year, or genre, or whatever. So we expect like Homeland to respond the same way, to be moving from a 9 p.m. slot to a 5 p.m. spot. We expect that to respect the same way like across programs. But each program has its own sort of inherent like natural appeal that's not captured by those covariates. And that's what this model is saying. We'll just do a quick comparison to ordinary least squares, because when I first looked at random effects model, it wasn't clear like exactly how it was different. So we've got some grouped data. We've got 3 groups, program A, B, and C, colored here. If we fit an OLS just onto the explanatory variable X, as you'd expect, it does like quite a good job of like minimizing that squared error like to the line, but it's disregarding all that group information. So now I use stats models here. So stats models also is a good mixed effects implementation for doing the random effects optimization. So it's just a change in objective, but it results in a completely different kind of sloped line. So this is just based on the fixed effects. And you can see what happens in the random effects model is it actually finds the slope that's common to all groups and fits like the within group slope the best. So you can see actually each group's slope is about -1. The global slope is about +1, but within each group it's about -1. So it's finding that like slope that's common to all groups. And then when you include the random effect, you get like quite good predictions. So you basically got, so the beta RE, that kind of captures like the mean structure of the data. And then you've got the delta parameters, which then give you your like inherent appeal above or below that average. And you end up with these colored lines showing like each within group prediction. So we'll look at some real data now. We're going to look at Homeland. So we'll just, this model was trained on like all of the data, but we're just going to focus on the Homeland predictions. So we're going to layer it on a bit. So this kind of blue shaded region is the training period. So up here we've got the ratings for Homeland in the training period. It's doing quite well. It's about 10% share. It's quite good. We'll layer on just the fixed effects prediction now. So the prediction just based on like time of day, genre, repeat status. And that kind of represents like the average. So that's kind of like what we would expect any drama on Channel 4 to be doing at 9 o'clock on a Thursday or whenever it was. So it's kind of doing actually a bit better than we'd expect from a typical drama at that time. We'll layer on the random effects prediction. So these are going to be the main prediction that we're interested in. So we'll see a few of these graphs now going forward. And always it's these red crosses that are really what we're interested in. These are the final prediction that we make. Now you can see the random effect is kind of capturing like the average deviation from the fixed effects line. So the final predictions in the training period are like quite well capturing sort of the mean structure of the ratings. And, you know, I'm relatively happy with this. You know, we're not under-predicting or over-predicting. We'll probably have nice, normally distributed residuals. So this is kind of what we want. But then we move into the test set. So these are now the kind of test period ratings. And you can see there's been like, not drastic, but a noticeable decline in the popularity of the show. We're down to kind of about 9% share. So on average, it's probably dropped by about a percentage point, which does mean that when we predict in the test period, we're persisting with the level of popularity that we witnessed in the training period. And without like a mechanism to kind of deal with this and adapt to changes in show popularity, we just stick with that and like naively end up systematically over-predicting. One nice thing, I suppose, that comes out of this is you can see the last broadcast is super low, but the model has, like, to some extent predicted that it's going to be really, really low. And this is because this final one, I think, was a repeat of the final episode. So that's completely as you'd expect, but it shows at least that kind of the combination of fixed effects and random effects is kind of, it has that nice characteristic where you can track show performance, but relative to like whether it's a repeat or not. So I guess the next thing is we really, really need to like address the fact that we just need to live with the fact that the distribution of show ratings changes as time goes on. So a standard way of dealing with like drift or kind of non-IID data is to downweight old data. So it's a simple idea, like your latest data point gets a weight of 1 and all the old data gets a weight lower than 1, typically like getting lower as you go back. It's really easy to calculate. And in fact, if you just decide you're going to have a fixed weight, you can do this recursively and just keep downweighting. You accumulate like the sum and the count of the data. You just keep downweighting the last time steps statistics at each time. And this is actually called the recursively squares algorithm. It's really fast, it's really simple, and it's actually quite good at like tracking changes in parameters. So you see with Homeland, when you do online RLS with like a forgetting factor about 0.925, you can see it's still not perfect, but it's a lot better than before. You can see still the first couple of episodes in the second season, we're still over-predicting, but quite quickly we come down and we're actually quite close to then the mean here. And then by the time we're here, we're basically right back where we want to be. So, I mean, that's kind of quick and easy. It's nice and relatively effective. It would be nice if we'd have like maybe some like predictive uncertainty and maybe uncertainty in some of our parameter estimates. So we'll move on and look at how you can do this in a Bayesian way. I don't want to give like a tutorial on like Bayesian inference, so I'm just going to really show the solution. Like, if you're interested in like conjugate inference of a normal, it's all out there. But essentially, the solution is this. All you need to do to have a posterior is track the sum of the data, the number of the data, and the sum of the squared data. And you accumulate these in like a matrix we're going to call V. and you just keep the count on a thing called nu. And then this is your posterior. It's actually a nice standard form of normal inverse gamma, even if it looks a bit scary, but it's not super important. But the point is, I guess, you only need to track a small number of sufficient statistics to have a posterior distribution, and it's the full posterior, and it's tractable, and it's quite nice to work with. And importantly, you can update those statistics recursively in almost exactly the same way as with the RLS algorithm. And you can see, so V0 and U0 are like your prior, but if you've an uninformative prior, they're probably going to be like the zero matrix or close to zero. And it just means that, again, in the same way as RLS, your latest observations are going to dominate your latest estimation of the mean, depending on how high of a forgetting factor W is set. So I think this is the main thing to take home, is that it's quite easy. I've even thrown in the code for doing this. Like, literally, these are just the 2 lines for the recursive update. You just extend the current observation by 1 and take the outer product of that with itself, and you accumulate those, and you use the forgetting factor. These are the 2 marginals on the mean and the variance. Any of you who've maybe got experience with this might notice that I've simulated 2,000 data points, but still the posterior looks quite flat. This is because I've put the forgetting factor of 0.95. So what this means is, actually, if you've got a forgetting factor of 0.95, the effective number of data that you're using is 1 over 1 minus the forgetting factor. So in this case, we're actually only ever using about 20 effective data points. And that's why this posterior, it's constantly limited. The forgetting performs this like constant flattening of the posterior. So we're never getting too certain, which is coming through because we've imposed this idea that we expect the distribution might change. So we never want to accumulate lots of certainty. So that's kind of just a natural outcome of Bayesian forgetting. So that shows it's pretty easy to implement in the simplest case. And then we can have nice kind of predictive distributions. So I've got slightly blue shade areas showing plus or minus 1 standard deviation of the predictive distribution. And it looks about right. You know, there's not really any real data landing too far outside of that. But the actual point predictions are about the same. The predictive distribution looks like this. It's a T distribution. So this is kind of important because we're going to come back to this later, and this distribution becomes key when we actually get to estimating a good forgetting factor from the data. The important thing, I guess, is the T distribution as you gain more data. So it's got a parameter called degrees of freedom. But basically, the more data you have, the closer it comes to a normal. But the less data you have, the heavier the tails. So you can see the blue case, we've only got 1 data point. Some really, really heavy tails. You've got density going really, really wide. And that makes sense because if you've only seen 1 data point, why would you be certain about anything? So that characteristic of the distribution is really important. So we'll move on to actually trying to look at maybe estimating forgetting factor. So just to see the importance of it, comparing what we had of 0.925 to if we set it to 0.5. I mean, in the case where it's 0.5, there's huge variance in our predictions, and we're really fitting to a lot of noise. We're almost just predicting whatever the last data point was, which maybe sometimes isn't that bad. Maybe in that case you want an AR1 model. But typically with TV ratings, they actually are quite stable. And you kind of want to suppress that noise, and you don't want to be letting like one outlier take your estimates right down. So it's usually suggested to like have a pretty high forgetting factor unless you have incredibly like fast changing parameters. So other reasons we want to estimate the forgetting factor is that I did a bit of cross-validation initially to set one for recursive least squares, and that did inform later when we had to choose a prior. But also, different shows can have different rates of change of their ratings. Like The Simpsons on at 6 o'clock is just never going to change. It's going to be the same pretty much forever. But stuff like Homeland, dramas that have less episodes, they're much more likely to change. So it'd be nice if we could have a different forgetting factor for each program. Also, if you've got a fixed forgetting factor, you can't actually track fast changes. So if your forgetting factor is fixed to 0.95, and then you've got a sudden drop in ratings, it's going to take you about 10 observations to acclimatize to that new level of popularity, because you're still using effectively about 20 data points. So if you've got a variable forgetting factor that looks at the data and says, maybe I should drop, then you can adapt to these sudden changes quite quickly, and we'll see that. So I'm going to digress now and just look at I've just got a couple of quite mathsy slides, because I think it's really interesting how you go from sort of just probability and information to like a practical and tractable solution. So we have to look at the interpretation of forgetting in the kind of the Bayesian context. So this is like the standard Bayesian filtering update. And that's kind of, this reduces to the Kalman filter if like you know this parameter evolution model. So this orange thing here is really important because it's the thing that we don't have when we're forecasting TV ratings that makes this difficult. If we had that, we could probably resort to a Kalman filter and have like the optimal Bayesian filtering solution, which would be nice. But the fact is we just don't have a model for like how the ratings are going to change from time now to the next, really. But the forgetting factor actually defines a bound on how far the posterior can change from now to the next time. So if you think, if I've got a forgetting factor of 1, I'm basically saying that the posterior cannot change until I see the next data point. So you can see what we're trying to get is the f of un plus 1 given only z1 to n. So if you've got a forgetting factor of 1, you're saying that it has to be the same as this. So if your forgetting factor is 1, you're saying this is the same as that, definitely. So your bound on the divergence between the two things is necessarily 0. And that's kind of a really important thing to recognize, is that because the forgetting factor defines this bound on how far the posterior can move between time steps, it's now necessarily a measure on the parameter evolution model, and we can include it as such here. So that's kind of an important takeaway, I guess. And it turns out that the posterior here that results from a certain W is the distribution that has the maximum entropy of all distributions that satisfy this bound. And the max entropy distribution is it's strongly argued by Jaynes and many others that if you don't know much about the posterior except that it belongs to a class of distributions, i.e. that it satisfies a bound, then the optimal and like minimum risk distribution is the maximum entropy distribution of that class of distributions. So if that's kind of over your head, and maybe I haven't explained it that well, that's sort of okay, but I guess the point is like forgetting has a really like rich and kind of satisfying justification as like an approximate distribution on a true posterior when we don't know the parameter evolution model. And then this leads us to possible ways of actually estimating it. So given what I've just said, the joint posterior on the latest parameter, mu n, and the latest forgetting factor is, so this is kind of just a big, long Bayes rule, but it's the likelihood of the latest data times the parameter evolution model, which is now a function of the forgetting factor, times the old posterior, times our prior on the forgetting factor. It's kind of long, but it's basically just Bayes rule. And you can integrate out the parameter mu, and which we can actually do because our posterior on that is a standard form normal inverse gamma, so we actually can integrate that out. And it turns out, so when we integrate all of the mu's here, you get the likelihood, or the posterior on the forgetting factor, is proportional to this likelihood, which is actually just the t distribution, which we saw, times a prior on the weight, or on W. So if we actually look, so we'll look at the likelihood now. So do you remember the t distribution that we saw? And we saw that it kind of flattened out when you did less data. So this is now the likelihood for our forgetting factor. And if you imagine, as you decrease your forgetting factor, you're decreasing the amount of data. So here are 3 different distributions given different forgetting factors. So the orange one is if we set our forgetting factor to 0.05, and we're basically saying we have almost no data, the predictive distribution at that time then is really, really heavy-tailed. And it'll give more density to observations in the tail. So what you're doing is you're saying, my observation at time n would have been this likely if at time n minus 1 we'd set forgetting factor to x, if that makes sense. So you can see if we set it really high, if we set it to 0.95, because the latest observation is kind of actually quite far away from where our mean was, forgetting factor of 0.95 becomes very unlikely. So this is kind of the formal kind of Bayesian estimation of the forgetting factor, and it's come through this like quite nice intuitive algorithm that says if the last observation was unlikely under our predictive distribution, then maybe the forgetting factor should be quite low. And that's kind of what this likelihood says, because that's the observation is quite far out. So we've just got a few other examples. So if we move it in, the likelihood of staying 1 remains closer. And then if the observation is right at the peak, then the absolute max is where the forgetting factor is 1 just here. But one thing we see is that the likelihoods are really flat. And this kind of makes sense because actually, if the latest observations come from an area of density, there's very little to say why it would have come from any other distribution. So if the latest data comes from an area that's quite dense in our current posterior, it's very hard to know whether it has come from that or a slightly different distribution. So again, this sort of, if you think about it, it kind of makes sense that the likelihood is flat, but it does mean that we have to impose quite a strong prior. And really, we do actually expect ratings to be relatively stable for quite long periods of time. We don't actually expect it to kind of go right down and right back up. We do expect long periods of stability. So this is the prior we've chosen. It's a mixture beta prior. So we've got a low component, which kind of has mass everywhere, but mostly a 0, and then a high component, which is by far dominant. I think we used a weighting of about 0.925 for this component and 0.1 for the low component. And this kind of just says we strongly expect the forgetting factor to be up around 1. I think the expected value of the prior is 0.93. So this kind of says that's strongly what we expect, but we are going to allow forgetting factors in other areas if the evidence is strong enough in favor of it. And then some of the posterior distributions resulting from that are here. So these are relating to some of the examples we gave earlier. So if the likelihood is like this, so this likelihood is peaked right towards 0. Because we've imposed that strong prior, we're actually still most of our masses up here, and we end up with an expected value of about 0.56 for the forgetting factor. And then it has to be very unlikely under the current posterior predictive to merit a drop in the forgetting factor. So we'll just look now finally at some real data. So Shipping Wars was doing pretty well for its first 10 broadcasts, share of about 4%. Then on the 10th broadcast, for some reason which we haven't been able to model, it just suddenly drops like a stone. So then, because of this, the model says that was so unlikely under our predictive distribution, we're going to say it's probably a change in the distribution of the data, and it drops. So the forgetting factor, which is these here, so they've been pretty stable up between 0.8 and 1, mostly about 0.9. When we see that drop, it drops right down to 0, and then our predictions, which are these red crosses, drop with it, and actually continue to sort of capture the mean structure of the data. And you can see the variance also comes down with it. So if we compare this to if we have a fixed forgetting of 0.925, you kind of see the benefit, I guess. So if we have a fixed forgetting factor of 0.925, you can see the predictions are just slowly trying to acclimatize to this new level of popularity, but there's always going to be a lag depending on your forgetting factor. And you can see as well, when the data changes, instead of attributing it to a change in the mean, it's been attributed to just a really big increase in variance. So you can see before the drop, the variance in the predictive distribution is, it's not that bad. As soon as this drops here, the model is kind of saying, suddenly our data is really highly variable. So you end up with bad predictions and also bad uncertainty estimates. Whereas on the left-hand side, you can see the predictions remain good and the variance remains about where it was, which is kind of what we want. And then just one more example is Gordon Ramsay. Similar thing. This one's not as clear-cut, which kind of makes it more satisfying, I guess, from the modeling point of view, that it's still quite good at tracking things when it's not insanely obvious that there's been a big change. So this is a little bit more of a slow downward trend in the ratings of Gordon Ramsay. We've got one case where it does drop quite low in the worst rating case. And you can see, again, the ratings drop. The uncertainty remains about the same, which is good. And again, we're doing okay in terms of predictions. And if we compare it with the fixed forgetting factor again, a similar thing happens where we've got suddenly our variance kind of just explodes. The actual point predictions aren't too much worse. It's about 23% error compared to 21 with the variable forgetting factor. But if someone was to ask me, like, how uncertain are we in this prediction, I'd be saying we're wildly uncertain. It could practically be anywhere, which actually isn't the case. The case of our uncertainty is much better reflected, I feel, by on the left-hand side, where most of the data is lying within one standard deviation, but not beyond. And that's pretty much it from me. There's a few main references that this was based on. One mainly on forecasting TV ratings by P. Danaher, and then a few on forgetting and recursive estimation by Carney and Kulvahi. The top one is probably the main one that describes estimating the forgetting factor, which in practice was done. I showed like numerically evaluated posteriors and likelihoods, but in practice we implemented just like quite a simple particle filter, which did that. But it was very, very simple. But yeah, so that was that. Any questions? I'd be happy to answer.
Hi. So here you're forecasting each program in isolation in a way, but is there any way you can think of extending this to modeling the interaction with what's happening on the other channels? I mean, maybe nothing happened on those massive drops. Maybe England was playing Germany on football at the same time.
Yeah, so it's a really good point. I have tried doing this. This bottom paper does actually propose to do that. So I tried models that modeled Channel 4, ITV, BBC 1 and 2. And I was expecting good results, and to be honest, it actually just, at the end of the day, it didn't make a huge amount of difference. Now, maybe I didn't look into it like deeply enough. I only looked at basically the global test score over like a year and a half, and it was basically the exact same as training and learning the model in isolation on Channel 4. But it would have been interesting to dive into maybe like individual program cases. And I suppose to some extent, if it was the World Cup or something like that, that's quite difficult to predict anyway. So if I was trying to base my predictions on Channel 4 on how BBC is going to do, I'd have to be predicting the BBC ratings quite well. And also, I don't think I had a World Cup in my training set, so even if I'd come up to a World Cup, the model may well have struggled to like capture that the World Cup is a huge sporting event to some extent. But yeah, it's a good point, and it's definitely, it seems intuitive that it would work. And to be honest, I probably haven't put enough work into trying to make it work, but I have looked into it a bit. Yep.
Have you looked at other models, like time series forecasting models that capture trend and seasonality and things like that?
So this was the main one I focused on. The main reason for that was probably, well, I suppose, the model is actually really, really good at capturing the seasonalities. Like, it's able to predict, like, the overall TV viewership, which is the main source of seasonality and, like, time trends. It's able to capture those really, really well. So what we've actually done is, I mean, I didn't want to go into, like, too many of the really small nitty-gritty details. What we've actually done is like a trigonometric regression, so 12 sine and cosine terms on the day of the year. So we've included those as features and then learned the parameters to accompany them, which it just worked really well at predicting like daily and yearly trends. So for the week, we've obviously got day of week dummy variables, and then we've also got hourly kind of dummy variables. But then for the yearly seasonality, it's that combination of sine and cosine terms. So we just used that, and it actually just worked really, really well. So I actually didn't try any of the more like standard methods, to be honest. Yep.
You mentioned random mixed effects models. Could you say about the levels, or was it just very basic in terms of where you leverage just the program you were looking at?
Are you talking about like at what level I had random effects?
Yes, exactly.
So here I kind of just described just having a program random effect. But actually I found what the best was to kind of have a different random effect for broadcasts of programs at different times, if that makes sense. So I had a random effect for like Homeland at 9, but if Homeland also aired at noon, I'd have a different random effect for broadcasts. So I actually divided the day into quarters. So any broadcasts between 6 and midnight got clumped into one group of random effect. But if the same show was broadcast earlier than 6, that would count as a different random effect. But that was the biggest, the most granular I went with it, basically, in terms of random effects. Yep.
This is obviously great for modeling something where, as things get more stale, you want to forget them more.
Yep.
How do you deal with things like seasonality, where you'd want to remember what happened last summer to trend? So like Bayesian remembering.
So I think an important thing in this model is that the forgetting was constrained to just the program-specific random effects. So, and also, if that program was last on in the summer, it will be remembered. But that's kind of, I don't know if that's really a good answer to your question, but I guess the main seasonalities are just captured by the fixed effects, which weren't forgotten at all. So they were treated as like completely stationary, and they were just learned at training time, and then it was treated as if they were coming from a fixed distribution. So it was only the past program ratings that were considered to be time varying. But definitely if there was like a case where a show exhibited being really popular in summer but not in winter, the model wouldn't capture that. So that would be another level of granularity. You could add random effects for like time of year and time of day, which are kind of like interactions to some extent. But we just stuck with programs within a certain part of the day. Yeah.
Any more questions? If not, let's
All right.
thanks.
Cool.
Carry on.
Thanks, everyone. Cheers.